better for me if I don't open the video because the internet connection is not good here. So
That is okay with me.
okay. So so do I have to share my screen or how? Hello.
I don't have anything to share for you.
Okay. Okay.
I have the PDF file. Sorry, I late a little bit. So I was so involved with the talk of Lucas that I forgot to put it on. I'm sorry about. Just 1 second, okay? I will
Okay.
do
All right.
it. Okay, just 1 second. I was very involved with the with his great talk. So I was, now it's okay. I will just go it, okay. And now I will share my screen, okay. And
Okay.
then I will show your beautiful presentation, okay. That's
Yeah.
okay.
Yeah. Sure. Yeah.
Oh, that's okay?
Yeah. Fine.
Fine? Okay.
Yeah. Thank you.
Sorry again.
Yeah. Yeah. It's okay.
Okay, you can begin.
Okay, so hello everyone. This is Avinanda Chakraborty from Presidency University, India. Here is my collaborator Anirban Bhattacharya. And firstly, I would like to thank the organizers for giving me this opportunity. Now let's come to my work. Can you please go to the next slide? Yeah, thanks. If central supermassive black hole of a galaxy accretes masses from its surrounding, then it is called AGN or active galactic nuclei. And most luminous AGNs are called quasars. And if we see through radio window, there are two type of quasars. One is a radio loud, which has a strong jet, and another is a radio quiet, which doesn't have strong as jet as the radio louds one. So the main goal of our work is we try to see are these two type of quasars same or different. So please go to the next slide. Perfect. Uh, Okay, so to look at, we first saw for the radio loud fraction, which is the ratio of radio loud quasar by the total number of quasars, and we can see that the radio loud fraction is increasing with FWHM of both broad H beta and MG2 lines, which means the radio louds are having high velocity broad line clouds. So we choose a higher velocity sample for our work and further check for the bolometric luminosity, black hole mass, optical continuum luminosity distribution, and the accretion rate distribution. Here we can see only the bolometric luminosity and black hole mass distribution. And for all of the distribution, we get that the radio louds are having higher values than the radio quiets one. So from bolometric luminosity plot, we can infer that the radio loud quasars are actually intrinsically brighter than the radio quiets one, because we have checked for the redshift distribution of these two types and they are actually identical. We have also inferred that the relation between black hole mass and jet from the black hole mass distributions, and also get a connection between jet and accretion disk from the optical continuum luminosity and accretion rates distributions. We have also found that from covering fraction distribution that the amount of dust around radio loud and radio quiets black holes are actually similar. So that is not the issue. So there are differences between these two type of quasars. Also, we have rechecked our results with other methods. All the detailed explanation are in my video recorded talk. Thank you.
Yes, thank you very much.
Yeah.
Our next speaker will be Nayak from the Technology Institute Park in India, also the National Institute of Science, talking about thermodynamical effects on FRW cosmological model for dark energy.
Hi, this is Dr. Vishnunkar Nayak from NIST India. Thank you, the organizer, for giving me this opportunity to present my research work on this platform. So my research topic is thermodynamical effect on FRW cosmological model for various dark energy. So in this discussion, I have considered the Einstein theory of gravitation by taking this FRW cosmological model and by taking the perfect fluid as my governing fluid. In this observation, we have considered two dark energy conditions and four energy conditions. By taking these 6 conditions, we have discussed some physical significance of different parameters like pressure, density, equation state parameter, etc. And from this discussion, we conclude that the model remain positive for both the cases. In view of energy condition, the assumptions the same result, and the strong energy condition violates that indicates an accelerating expansion of the universe. Next slide, please. Here I have taken two conditions for the different cases of dark energy, and is our field equations containing more number of equations with less number of equations with more number of constants. So we have assumed here two assumptions. One is pressure density equation state parameter, and second assumption is about the time varying deceleration parameter. And by taking this, we have presented the geometrical interpretation of the different parameters. Next slide, please. Yeah. In this case, we have, as I have considered here, FRW cosmological model, and as my main focus is the thermodynamical effects. So by combining the first law and second law of thermodynamics, we have considered this equation, and this is my one assumption P equal to gamma rho. So for different values of gamma rho, as we are getting different conclusions as we know that for gamma equal to 0, if we will consider gamma equal to 0, then we are getting the dust model, and for gamma equal to 1/3 we are getting radiating model, and for gamma equal to -1 we are getting a vacuum model. And also when gamma less than 0, it is considered as an accelerating expansion of the universe. And also there are some intervals, considering some intervals, like if gamma lies in between -1 to 0, we get the quantized phase, and when gamma less than -1, it is phantom phase, and for gamma equal to -1, this is quantum phase. So by taking these important points, we considered here this assumption, and from this geometrical interpretation, what we conclude, I have taken here 3 cases, one for open and another for closed. So in this figure, you just see here from this open universe is violates, but the quantized phase for all the universe, because you see here this is in diverging nature, and from these two, all the 3 cases are not violating, and in this case only the open universe is violating. So it represents the phantom phase. Yes, sir. What the phantom phase of the universe. So FRW cosmological model in Einstein theory of gravitation, we have considered in this case the time varying dark energy states in 2 different cases, and from which we got the accelerating expansion of the universe. Also from our investigation, our model shows a universe of finite lifetime. All obtained results, whatever we discussed, are consistent with the observational constants point of view. Thank you very much.
Thank you very much. And it looks like you have some very good work going there.
Stephen, just 1 second, because I have to put in full screen, okay? Just 1 second.
Okay.
Não, não vai. Não está indo. Agora não está indo. Não está indo. Agora não vai, a tela cheia não sai. Agora vai. Deixa eu ver se eu consigo lá. Ah, agora foi. Now it's okay.
Now it's okay. Okay. Next, we will hear from Dimitar Hadjimichef from the Federal University of Rio Grande do Sul in Brazil. Dark photons in a Higgs-Stuckelberg model for dark matter.
Well, hello. Thank you. Do you hear me?
Yes.
Yes.
Okay. Well, hello. My name is Dimitar Hadjimichef. I'm from URGS, Universidade Federal do Rio Grande do Sul, and I will talk to you briefly about dark photons and the Higgs-Stuckelberg model for dark matter. This study was carried out together with Alexander Lunks dos Santos, a former PhD student. The model proposes to extend the standard model by including 2 new gauge sectors, which are represented by 2 new vector bosons. The name Higgs-Stuckelberg is related to the mass generating mechanism. First, the non-abelian fields get their mass from the usual Higgs boson, while the new vector bosons acquire their mass from the so-called Stuckelberg mechanism. Next slide, please. So the motivation to review and revisit this model came from a recent result from the Xenon collaboration. They presented a low energy access that could be interpreted as dark matter. Actually, they presented 3 possible explanations. First, the signal could be a solar axion, or second, the signal could be a neutrino with large magnetic moment. And if everything goes wrong and the signal is a false positive, a possible contamination from tritium atoms. This is the point where we argue that this signal could be understood in principle in the context of the Higgs-Stuckelberg model, which I shall review briefly some of its results. In the lower part of this slide, you see the extra particle content of the model. There's this chi particle, which is a fermionic singlet that carries both a small electric charge and also a dark charge. There's a massive vector boson, the Z prime, and also a massive boson, the dark photon. The chi particle lives in both worlds. It actually interacts with the standard model constituents through, for example, coupling to the electric charge, and also with particles of the dark sector. Next slide, please. Next slide. Thank you. As an application, we studied an astrophysical problem related to the anomalous energy loss in certain stars, such as the pulsating white dwarf G117b15a. This anomalous cooling mechanism could be understood as the emission of invisible radiation, which Corsico, Kepler, and Alejandra Romero considered to be an axion. They inferred from this analysis the axion mass of approximately 17 milli-electron volts. We did a similar analysis, only switching the axion radiation to that of the dark photon. In this case, the stellar mass was modified to be a mixture of ordinary matter with chi fermions. The chi particles converted the photon into dark photons by a Compton-like process, where in the figure you can, at the left, you can see the white dwarf energy loss as a function of the temperature. The black curve is a reference curve coming from the axion. The colored curves are for the dark photon for different mass values of the chi fermion. The mass range goes from 1 to 10 keV. Finally, we believe that if we believe in these results, we see that a low mass particle such as the chi fermion interacting with electrons, for example, could in principle produce an excess like the one observed in the Zeno experiment. But to be sure, as a quick check of this idea, we must calculate the background in the presence of the chi particle to see if we can reproduce, of course, the Zeno results. But this will be done in the near future. So we have to be fast before they realize that their measurement could be wrong. Thank you very much.
And thank you very much. Our next speaker is Quintero Angulo from the University of Havana in Cuba, speaking about quantum magnetic collapse of a partially bosonized NP gas, implications for astrophysical jets. And we can't hear your audio right now, Gret. It's not showing your mic is being, yeah, there it is, it's on. I'm not sure why we can't hear you.
Can you hear me now?
Yes, yes, we can hear you loud and clear.
Maybe
Okay.
I think I have some problem with the microphone and the...
No, you sound good now.
Oh, okay,
So
perfect.
please begin.
Yes, I think I can. Okay, well, hello, and thank you very much for giving me the opportunity of sharing my work in Iwara, here in the distance, but still together. This afternoon, afternoon in Havana, I will talk about the quantum magnetic collapse and its connection with astrophysical jets. Quantum magnetic collapse is a phenomenon that is experimented by magnetized quantum gases and consists on the differentiation between the pressures that the gas exert along and perpendicular to the magnetic field axis when this gas is under the action of a magnetic field. Under certain conditions, one of the pressure of the gas can be negative or less than zero even, and is the pressure that is negative, we have is the one that is perpendicular to the magnetic axis. We have found that this phenomenon could be in connection with astrophysical jets. Next slide, please. Okay, thank you. So astrophysical jets are this stream of collimated matter that are ejected by several astronomical objects. The physical mechanism behind jets are supposed to be all the same, disregarding which is the origin, that may be a star, a galaxy, etc. And our proposal with this model is that the role that magnetic field plays on jets is played through the quantum magnetic collapse in the perpendicular direction to the magnetic field, as we show in this diagram. So to begin testing this hypothesis, we consider a toy model, which is what we have called a partially bosonized NP gas. And this gas is just a mixture of neutron, electrons, protons, and pair of protons and neutrons. And we will ask, is this gas that in principle could be inside a star or a compact object in general, can have a negative pressure in total or for one of its components in astrophysical conditions. And by astrophysical conditions, we mean magnetic fields and baryon densities in the order of those of neutron stars. And we want also know if this collapsed gas can have a parallel pressure strong enough to overcome the gravity of the object where it is been. And also we want to know if once the matter leaves the star, the magnetic field is strong enough to keep it collimated. So what we found is, in fact, that the answer to these three questions is positive. Next slide, please. Because depending on the magnetic field and the particle density, the electron, proton, neutron, and pair neutron gases may collapse, while the gas of pair protons is always stable. Also, these collapsed gases can have a pressure parallel to the magnetic field strong enough to overcome the gravity of a compact object, and the magnetic field they produce is strong enough to keep it collimated once they leave the star. In addition, we find that the difference between the pressure of this mixture of gases in the collapsed regime is of 4 orders, so it's strong enough to account for a difference, a structure elongated and so different from a star that is more rounded or so like a jet. And also we think that the proposed mechanisms could be extended to more realistic matter models as long as they contain gases that can suffer a transversal magnetic collapse, and that is what we want to do in next step. In the video recorded presentation, you can find all the calculations and details, and if you're interested, you can also write to us by email or so. Thank you very much.
Thank you very much, Gretel. Jose is not here today, Cesar. So we will next go on to Rafeel Riaz from the Universidad de Concepción in Chile, talking about the possible role of fragmentation accretion on the stellar initial mass function.
Yes, okay. Rafeel is not here also?
Yes, I'm here. Can you hear me?
He's here. There he is.
Yes, perfect.
Can you hear me?
Yes, it can hear you.
Yes, it's okay.
Okay. Hello, everyone. This is Rafeel Riaz from University of Concepción, Chile. And my work is actually addressing whether the stellar initial mass function is actually universal or not. It's always under debate whether the universality is there or not. So we try to address this particular phenomena of a stellar population with the help of the two fundamental regimes, any star-forming gas collapsing. These two regimes are the fragmentation and the accretion-dominated regimes. So we try to address this. A quick concept of the stellar initial mass function is that whenever a new population of stars coming into existence, it always come with some mass distributions. High masses are small in number, while the low masses starts increasing up. And when you reach to a certain level of low masses, if you go beyond that, the number of stars again starts decreasing. So that's the stellar initial mass function, what we talk about. Next slide, please. So to address this, actually, we consider the cosmic microwave background radiations. And we consider this particular aspect as the dominant source, which can affect the stellar environment and regulate the thermal conditions prevailing in star-forming regions. And we try to analyze the CMB contribution towards the star formation, and hence it may regulate the stellar masses coming into any population. So what we did is we try to consider 5 models, starting from 10 Kelvin to 50 Kelvin as initial temperature states of these collapsing clouds of gas. And when we say 10 Kelvin to 50 Kelvin, we actually also cover a range of redshift from somewhere around 2 to 17. With this, it means that we actually try to cover a range of redshift, which means a cosmic stellar formation history. And we try to see whether the cosmic microwave background was really something that regulate the star formation. And since the collapse of a gas is actually following the thermodynamics, so to carry on with the thermodynamics, to follow this thermodynamical feature of the gas collapsing, we followed the barotropic equation of state. And if you see on the left for the 10 Kelvin gas, which is the final state of the collapse of our simulations, we come to know that if the gas is lower at the initial temperature and it starts collapsing, we found that there are quite a number of stars coming into existence. But on the right-hand side, which is the 50 Kelvin core, which mimics the high redshift environment, we found that not many stars coming into existence, but whatever coming into existence, they are more massive in terms of their masses involved. So that's the very first conclusion, that in a young universe where the temperature was quite high, it's difficult for a star-forming gas to attain lower temperatures as initial temperatures. And when these star-forming gases start collapsing, they actually form more massive stars than their counterparts, which is the present-day star-forming conditions, where you can have 10 Kelvin gas as the initial temperature of the gas cloud, and then it starts collapsing, forming quite a number of stars, but mostly they are low in masses. Can you go to the next slide, please?
And we are in our last minute.
Okay. So we try to follow the mean masses of the entire distribution of all these 5 models. And we come to know that if you reach to a specific star formation efficiency, which is around 5% value, you see that the more higher temperature environment, initial higher temperature environments, they are going to yield more massive stars. The green pattern is actually the high redshift environment, more thermal agitation is there, and they are producing more higher mean masses. Whereas their counterpart, which is the red or the blue one, they are forming masses for the stars very low. So the star formation efficiency is also very critical when you try to understand the CMB contribution towards the stellar initial mass function. You can go in much detail if you follow my presentation, which is already a recorded one. That's all. Thank you very much.
And thank you very much. And Cesar, the remaining 2 speakers are not here today either. So, Benno, if anyone has questions for any of the speakers, you can enter them in the Q&A by name. And
yeah, all the questions have been answered until now.
So it looks like we are caught up. Cesar or Peter, is there anything else that you want to bring out before we conclude today?
Cesar just is showing the program for for tomorrow.
Yes,
Yeah,
I will show that. Okay, this is the program. Just a second. Yes. This is the program for tomorrow, yes?
It was. It's gone now.
Okay.
No.
Can you see?
No.
How? Why not?
It was there at first, but now it's just a gray screen.
Yes.
Before it was there, but the letters are very small.
Yes. Okay. They are too small. Yeah. Yes. It's hard to see. Yeah. Okay. Let me see. Do the following. I put the other version of the program. Okay. More easily to read. Just 1 second. Okay. I think this one can be seen in a more easy way. Just 1 second. Yes?
No, it's still gray.
How could that be? I will stop sharing and start again, okay?
Okay.
Okay. So let me do that. Yes. Okay. I will share screen. Share screen. Share screen. No, sorry, doesn't work.
We see
yes? Yes?
Yes.
It does work?
It does work. You have only to go to Wednesday now.
Okay, okay.
Now something has changed.
Yes, the program.
Yeah.
Okay, the program for tomorrow. Okay, we start with Sandoval in the morning. Then we have Ulysses. Matthias, Danny Page, Spotlight Session 4, Elena Bratkovskaya, and then Horst Stocker, and then the parallel session discussions for tomorrow. Okay?
And that wasn't really shown, but if you stop your screen share, I'll share mine because I have what you sent me a few minutes ago on my screen.
Okay, I will do that. I will do that. Okay.
And
It's good. It's good also for us to check if everything is fine or not.
Now you can talk to this.
Yes. Well, this is the program for tomorrow. You can see with more details the program for tomorrow. Yeah. So we have the chair is Peter Hess, co-chair is Thomas Boller. Then we have the presentation in the morning of André Sandoval. Then Ulisses Barres de Almeida. Then we have Matthias Hanausk, and then we have Danny Page. Then it ends at 10 o'clock, the last talk. Then we have a break, and then we have this the Spotlight Section 4, share Mariana Vargas and Gabriela Piccinelli. Then we have another break with video synthesis in both breaks. And then we have at 11:30, again, Peter Hess and Thomas Boller as chair and co-chair. We have the talk of Elena Bratkovskaya, and following the talk of Horst Stocker. And then we have the parallel discussion session with the participation of Abdel Diab, Abdel Taufik, Alejandro Cabo Montes de Oca, Enchier Fani, Igor Kulikov, Li Jing Shao, Surajit Chattopadhyay, Violeta Sagun, and Zifugal. This is the program for tomorrow. Yes, I think it's correct, no mistakes.
Yeah.
Yeah? Yes. Yesterday I made a mistake.
It's correct. The poster at least is correct.
yeah. Yes, of course. I understand your point. sorry for today. I was, trying to do my best with so many, well, doesn't matter. We solved the problems. This is important. Well, I think it was a great day today, yes?
Yeah,
Great
it was
day.
fantastic.
Fantastic day.
So you will see you tomorrow, no?
Yeah, we'll see us tomorrow, yes? Okay. Yeah.
Mariana, is the list for the poster presenters the same? Has it changed at all?
I will have to give to Mariana some present, something to honor.
Steven, I will send you again the list just in case. But yeah.
So I'll take that. And I'll take what Cesar has put together here, and I will get those all set up for tomorrow morning.
It's good that we do that at the end because we can check everything together. Yes.
Yes.
It's a good idea. It's a practice, and there is something that we have to remember tomorrow also. Not only to ask people to use the questions and answers only for questions, not general comments, and also to ask the panelists to answer the questions addressed to them. Yeah, this is very important also. So I think we should do that tomorrow, from tomorrow on, to ask the panelists to for instance, today David told me, "Oh, I made my homework." Yes, fortunately, I have no question for Lucas, but certainly he would do the same. And I think this is important. Yeah.
Okay.
Okay.
Very good.
We'll see you.
Okay, see you tomorrow.
Okay.
Have a good evening, and we'll see you in the morning.
Yeah, see you in the morning. See you in the morning.
Morning or afternoon, depending on where in the world you happen to be, even evening.
Okay.
Yeah, that's video
Thank
meeting.
you all. See you tomorrow.
See you tomorrow. Stephen, just one thing before you go. I will send you the list of mails for tomorrow. So please use my list just in case.
I'll wait for your list just in case, because that'll be the most up-to-date information.
Yeah. Okay. Thank you. Bye-bye.
Bye. Okay, bye, Stephen.
Bye, everyone.